All right, the unit that we're starting today is about trigonometric ratios. So we actually are, even though we've been working on geometry, there is a crossover with some trigonometry in geometry. We're going to start you off with a basic introduction to trigonometry through these trigonometric ratios. And we'll be talking about those this unit. So we should have already put our name on our packet. Put our period number there. And then as always, go to that table of contents page where those essential questions go. The first essential question: how are special right triangle ratios related to trigonometric ratios? So how are special right triangle ratios related to trigonometric ratios? The second question: why are sine and cosine of complementary angles equal? And sine is spelled S-I-N-E, and cosine is C-O-S-I-N-E, of complementary angles equal. What does complementary mean? We defined that term last unit. What does it mean if angles are complementary? They add up to 90 degrees. So just reminding you that this term here, when they're talking complementary, that is telling us two angles that add up to 90 degrees. So again, important. That's why vocabulary is so important, that we keep up with that. The third question: how can I use trigonometric ratios to find side lengths and acute angle measures? And question 4: if X is an acute angle, then what is the range of values of sine x. Now the abbreviation of sine is sin x. Cosine x, the abbreviation is cos x. And the tangent of x, and tangent is abbreviated tan x. Those sine, cosine, and tangent, you should see that on your calculator. Those are keys that we have not dealt with before that we are going to be addressing in this unit. All right, so we are going to get to the first lesson today. So up above here in our table of contents where it says notes simplifying radicals, today is the 10th. So we're going to put that date in there, and then we're going to go to page 7 so that we can work on that lesson. So again, like I said, a lot of this unit is going to be calculator work, but there's also a skill that we need to know how to do without a calculator, which is simplifying radicals, because it does come up on standardized testing where they don't always give you a calculator that will simplify the radical for you. You need to understand how to do that. And we're going to be applying it in a couple different ways. But to know how to simplify radicals, we first have to start with talking about perfect squares. So a perfect square by definition is the product of a rational number multiplied by itself. And you see, I'm going to have you fill out a chart here. Now, I really think you should know the first 20 perfect squares. This one goes to 21. It was 3 columns, so it doesn't hurt us to add 21 in there. Because the more perfect squares we can recognize by sight, the easier it makes it in simplifying these radicals. So starting off here, starting with 1 squared. So Gary, what is the value of 1 squared? In other words, what is 1 times 1? So if I move that number, that square, under the radical, the square root of 1 is 1. Lavana, what is 2 squared? So the square root of 4 would equal 2. Square root is asking what number times itself makes this. When we're doing the square root, we're undoing the square. Sergio, what is 3 squared? So the square root of 9 would be? Layla, what is 4 squared? So the square root of 16, 4. Okay, I'm going to pause there because I want you to go through and finish filling out the chart, and then we will double check to make sure we have all the correct answers. All right, so Maya, what is 5 squared? So the square root of 25 is 5. Gabriel, what is 6 squared? So the square root of 36 is 6. Leah, 7 squared. And the square root of 49 is? Valeria, 8 squared. So the square root of 64 is? Ruby, 9 squared. Square root of 81. Stephanie, 10 squared. Square root of 100. Isabella, 11 squared. square root of 121. Ariana, 12 squared. And the square root of 144. Jocelyn, 13 squared. 169. The square root of 169. Alex, 14 squared. And the square root of 196. Lily, 15 squared. And the square root of 225. 15. Jacob Prado Martinez, 16 squared. And the square root of 256. Julian, 17 squared. And the square root of 289. Michael, 18 squared. $324, and the square root of 324 is 18. Matthew, 19 squared. And the square root of 361, 19. Devin, 20 squared. And the square root of 400. Alexandra, 21 squared. 441. Oops. And the square root of 441, 21. Now, the reason I go through that is I want you to see the relationship between the square root and the number we're looking for. Because what we're doing today is it's about trying to find perfect squares within other numbers. If we can recognize these top 21 perfect squares, it makes simplifying square roots a lot easier if we know these relationships and don't have to rely on a calculator for all this. Now, we can get it all the way down to its prime factorization if we don't recognize these. But this just helps if we're aware of these perfect squares here and what their square roots are. It makes it a lot easier for us to simplify the square roots. So I have the steps listed there for you that we're going to be doing here. We're going to use a factor tree to find the prime factorization of the number under the radical. Group together any numbers that are repeated in the factor tree. Each group of 2 represents a perfect square. For each perfect square, take the square root of that number, leaving the other numbers under the square root. Multiply all numbers together outside of the square root and multiply all numbers together inside the square root. I know that might seem a little confusing right now, but you see as we get the process going what all that means. So the first one they're asking us here is for the square root of 175. Is 175 a perfect square that we just listed in our list above? No, so we know it's not a perfect square. So now the goal is to see, can we find some perfect squares within the factors of 175? So if I start a factor tree for 175, I'm looking for 2 numbers that I can multiply together to make that. Aaliyah, what are 2 numbers, or let me go back a step. What is a number that I know will divide into 175? 5. 175 ends in 5. I know that 5 goes into anything that ends in 0 and 5. So I know 5 is going to be one of my factors. So Renessa, what do I have to multiply times 5 to get 175? And I can find that by dividing. What is 175 divided by 5? 35. So I can do 5 times 35. 5 is a prime number, so I know I cannot break it down any further. The only way to make 5 through multiplication is 1 times 5. So now I have to look at 35. And Victor, what are two numbers that can multiply together to make 35? 7 and 5. I'm going to do 5 times 7 just so it's a little easier to show. The numbers don't have to be next to each other, but because this is the first one I'm showing, I'm going to write this away so it's easier for me to circle. So what it means by circle the numbers that repeat, so I have a 5 times 5. The value of 5 times 5 is 25. Is that a perfect square? Yeah, that's in my list. So 7 is prime. I can't break that down any further. So I can say that the square root of 175 is the same thing as saying the square root of 25 times 7. That 25 comes from this 5 times 5. That's where I'm getting that 25 from. So that means it's the square root of 25 times the square root of 7. I can break each factor down into its own square root. And now, Danny, what is the square root of 25? It's in our chart. What is it? 5. So I have 5 times radical 7. So the square root of 175 equals 5 radical 7. I don't have to write the multiplication between them. This is just like a radical sign acts the same as a parentheses, where if they're right next to each other, it's telling us to multiply. So that would be the simplification of the square root of 175. So really, if I knew that 25 went into 175, I could have broken it down faster. But you see, it doesn't matter. It's not about doing it faster. It's about doing what you recognize. We're looking for those perfect squares. If I can take a perfect square out of the number, and sometimes we're going to see in an example where it's possible to find more than one perfect square within a number based on how we're breaking it down. So number 2, the square root of 45. So I need to start by doing a factor tree of 45. And Destiny, what are two numbers that multiply together to make 45? 5 and 9. 5 is prime. I can't go any further. But what do I know about 9? Three times 3, so I already know that 9 is a perfect square. Now, could I break it down and show the 3 times 3? Absolutely, but I'm looking for the perfect square, so if I found the perfect square there, the square root of 45 is the same thing as saying the square root of 5 times 9. So the square root of 5 times the square root of 9 equals the square root of 5 times 3. We know that the square root of 9 is 3. So the square root of 45 is 3 radical 5. We always put the number, whatever we take out from under the radical, whatever perfect squares we find, they always go out front. And then we do the radical and whatever's left. So the square root of 45 is the same as 3 radical 5. If you were ever wanting to check your work, you could square the number outside and take it by the number inside, and you should be back to that number. So 3 squared is 9. 9 times 5 is 45. So I'm back to where I started. Now, some numbers are smaller than others, making it easier. Number 3, the square root of 252. So I need to do a factor tree of 252. So 252 is an even number. What do I know that divides into every even number? 2. So if nothing else, if it's an even number, I know I can start with 2. That's always a starting point. And if I know that 2 goes into it, I can take 252 divided by 2, and what is that number? So I know that 2 times 126 gets me to 252. 2 is a prime number. It's the only even prime number, because the only way to make 2 is 1 times 2. Every other even number after 2 is divisible by 2, which makes them composite numbers. So 126, again, some of you may realize there's other numbers, but it's an even number, so I know 2 goes into that. So 2 times what? So 2 times what would give me the 126? 63. So again, there is a set of numbers times itself. So I know I have one perfect square there. Okay, 2 times 2 is 4. So I have one perfect square represented there. But what about 63? What two numbers multiply together to make 63? So 3 times 21. 3 is prime. I can't break down 3 any further. But what about 21? 3 and 7. So again, I get another set of perfect squares. 3 times 3 gives me 9. So really, the square root of 252 is the square root of 4 times 9 times 7. Again, the 4 comes from those 2 2's. The 9 comes from the 2 3's. And the 7 is the only thing I did not circle. I have to make sure I account for everything. So this would equal the square root of 4 times the square root of 9 times the square root of 7. Square root of 4 is 2. The square root of 9 is 3. I cannot simplify the square root of 7. So now I have 2 times 3 times the square root of 7. Now this is where it gets down to where I said multiply all numbers together outside of the square root. We have a 2 times 3 on the outside. So this is 6 times radical 7. So the square root of 252 equals 6 times the square root of 7. So had I known 36 goes into 252, 36 was really my perfect square that I was looking for, but it's okay that I found the 4 and the 9 to get me there. That is perfectly okay. Now, what happens if there's already a number outside of the radical? We need to address that situation because that does happen. How do I simplify if I have a number outside of the radical to begin with? So on the next page, we see the example 2 radical 112. Now, as far as the factor tree goes, I'm just looking at the 112. The 2 will still move over into my answer. It's not like the 2 disappears and goes away. So I start with, I want to do that factor tree of 112. Again, I'm worried about I'm trying to break down what's under the radical. I know that there's a 2 out there, so when I do that equal sign, this 2 here is automatically moving over into my answer, so it's 2 times something. So we can't forget that number, but it's not part of the factor tree. So what 2 numbers can I multiply together to make 112? So 2 times 56. Again, it's an even number. So I know that 2 goes into it. 2 is prime, so I can't break down the 2 any further. What about 56? What 2 numbers can I multiply together to make 56? 7 and 8. Could I have gone with 2 times something again? Absolutely. There is more than one way to do a factor tree, though there is only one correct answer from the factor tree. 7 is prime. I can't break down 7 anymore. What about 8? How can I break down 8? 2 times 4. Now, this is a good example. I have 2 2's. Just because they're not next to each other doesn't mean they don't count. I can still, this is still 2 times 2, so this still gives me a 4. And then it just so happens I have another 4, because again, this is a perfect square. So I already brought my 2 over times the square root of 4 times 7 times 4. The big thing, do not forget the numbers you did not circle. Okay. And it is possible sometimes you'll have more than one number that you did not circle. You have to make sure you are accounting for everything that is at the end of a root. So then this becomes 2 times the square root of 4 times the square root of 7 times the square root of 4. So 2 times square root of 4 is 2. We can't break down the square root of 7 times 2. Even though that last 2 is after the square root of 7, it's considered as being part of outside of the radical. So this would really be 2 times 2 times 2 times radical 7. And what do I get when I take 2 times 2 times 2? 8. So I have 8 times radical 7. So 2 radical 112 is equal to 8 radical 7. So number 5, negative 6 radical 288. Again, the negative 6 is going to move over into my answer, so it's not like we're ignoring the negative 6. We know it's going to be part of the answer, but for the factor tree, we're only worried about what's under the radical, which is that 288. I'm going to pause for a moment to give you a chance to see if you can break down 288, and then we'll come back and check on it. All right, so how can I break down 288? What are 2 numbers that I can multiply together to make 288? Two times 144. Now, in going around and looking at answers, a lot of people kept going from here, which is fine, but could I have stopped right here? Yeah, because what do I know about 144? It's a perfect square. So the whole point is we are looking for perfect squares. 144 is it. Now, I'm going to keep going because I know a lot of you kept going, so I want to show how we can still get there. If you stopped here, great. We're still going to get back to where you were, but I did see a lot of people keep going, so I want to make sure just to show in case we missed the perfect square there. We could have gone, then this would get us to 2 times, what, 72? Now, I also did see some of you break down 144 to 12 times 12. So you showed me that you understand it's a perfect square because anything times itself. But then you kept going. But again, here's one set of 2's. So I know that that represents a perfect square of 4. 72, I saw people going, okay, well, 2 times 36. Here was another opportunity to stop because 36 is a perfect square. But if we didn't recognize it, it doesn't help us. Some of us kept going and said, well, that's 2 times 18. Okay, so there's a second set of 2, which is 4. And then we said, well, 18 is 9 times 2. And 9 is 3 times 3. Some of us went all the way down to here, which is fine. But we could have stopped. Again, our whole goal is to find perfect squares. We could have stopped at 2 times 144 because we know the square root of 144. But for those that went all the way here, don't forget there is 1, 2 that we did not circle. So this is -6 times the square root of 4 times 4 times 9 times 2. So -6 times the square root of 4 times the square root of 4 times the square root of 9 times the square root of 2. So we have -6 times 2 times 2 times 3 times the square root of 2. So -6 times 2 is -12 times 2 is -24 times 3 is -72 times radical 2. So I'm not going to have room to rewrite the whole thing here. So this is going to be -72 radical 2. We'll pick up with this tomorrow.